So the paper today is the Swin Transformer. So the long name is Hierarchical Vision Transformers using shifted windows, and that's how the name Swin comes. And these are the authors, and they are all from Microsoft Research Asia. And when we consider this paper, this is actually an architectural improvement for the existing VIT architecture. So what we will do is we will initially look at the background and then slowly build up towards what they have done. We need the background to understand why what they have done is working. So initially we look at human vision and CNN. So when we consider human vision, we are seeing this kind of a layered architecture. So these are the different layers, and when we travel through these layers, in the initial layers we will be identifying small features like edges and corners, and then when we go deeper, more complex features will be identified, and also the receptive field size will also increase. The receptive field means what area in what we see activates as a single cell. In the initial layers only small features identified, therefore the receptive field size is smaller, and when we go deeper it will increase. And a similar architecture is seen in the CNNs also. We know in the initial layers it will identify things like edges and corners, and when we go deeper, more complex features will be identified. And when it comes to CNNs, the main features of CNNs are translation, invariance, locality, and pooling. So you can read more about this in these articles and this paper, and we will go deep and have a discussion about these main features of CNNs. So the first is translation, equivariance, and invariance. So what that means is wherever the cat is in this image, the model should be able to classify it as a cat. But what translation invariance means is that wherever the cat is, the next layers, the feature representation should be the same. But we know it's not going to be the same because depending on the position of the cat, it will vary. But through pooling, when we go deeper and when it goes through pooling layers, then in deeper layers it will have the same representation. So that's why we are saying translation invariant, but invariance comes with pooling. And then the next key feature is the locality. So what we are doing with locality is we are telling the CNN to look at local neighborhoods and calculate features. And then pooling, we know what pooling is we are only taking the highest, mostly activated features into the next layer. And then this hierarchical receptive fields thing is also there in CNN. So what happens is this layers, this feature will be seeing the whole image. So that's what happens, this feature will be seeing this whole part in this image. So that's why we have this hierarchical receptive fields also in CNNs. But as any system, CNNs also have their own flaws. We saw this today, adversarial attacks. So given an image of a panda, it can classify it correctly, but when we add a noise, it starts to identify or classify it as a different thing. So is this the end of CNNs? But don't other systems also have flaws? When we consider human vision, now this image is an image of a cat, but now this one starts to look like a dog, right? So the only change which we have done is we have drawn an outline around the nose, and it starts to look like a different thing. So this happens because of a certain type of bias in any visual system, and we will discuss that later. So then meanwhile, transformers came into the picture in 2017, and it came into the NLP tasks, and we all have seen this. There are input and embeddings. The embeddings for these words do not have contextual information, and when we send it through attention block, we will get embeddings which contain the contextual information. And then in 2020 we are seeing the first most noticeable paper. It's not the first, but it was the first noticeable paper. The VIT came into the picture, and what that does is like it breaks the image into patches and convert it into embeddings and send through this transform architecture and get representation. So what it's actually doing is like it's learning the relationship between patches in order to classify it. And so by the looks of it, we can see that things like translation and invariance and locality are not here, which are like baked into CNNs. Those things are not here in transformers. And also like these are global from the start itself, right? It's like considering the relationship between patches right from the start. But CNNs, we saw that like it only in the deeper layers it will start seeing the whole image. And then we discussed this, I think Gavin also discussed this, that transformers have weaker inductive biases. So we will like go into depth and discuss what that means also. And then researchers have been arguing whether actually transformers are more closer to human vision. We saw that CNNs and human visions had many comparisons, but they are arguing whether transformers are also like human vision. And I will get us like start to that discussion. So we are saying VITs have more shape bias. That means like VITs will be like understanding relationships between these small features, right? So like combinations of features like corners and edges build up shapes, right? So that's why we are saying transformers have more shape bias. And we saw in the earlier presentation as well, CNNs will be having more texture bias. The reason for that is it's looking at pixel by pixel, right? That's why CNNs have more texture bias. And we will now go into a more deeper discussion. Before that, you can read this article and this paper. So I have extracted some information from those. And so we are saying VITs have less inductive bias. So what is inductive bias? Now let's say we have a set of training data and a model, and we want to like guide it towards a good optimal point. To guide it, the kind of biases we add are inductive biases. So like for an example, in CNNs we are saying, okay, look at local patches, okay, do pooling. So those are the kind of inductive biases which we are adding. But we know that in transformers we do not have constraints like that. So that's why we are saying transformers have weaker inductive biases, but actually it's not that it doesn't have inductive biases, but we are saying like there's no like predefined patterns or structures, do this. We are not limiting it like that. So because of that, the transformers have the capability to learn more complex relationships. But in order to learn complex relationships without any guidance like this, it will obviously need more data. It will have to see more data. So that's why even in my last presentation I said transformers are data hungry. So the reason for that is this. And then now look at this. So when we these are different classes, and this side shows the to classify these classes, the decision is based on shape, and to this side it's based on texture. And when we consider humans, our decisions are mostly based on shape. So that's why in the previous case, that cat image, when we slightly change the shape, we started seeing it differently. So our human system has more shape bias. That's what this is showing. And look at this VIT.
How have they obtained those diamonds?
You mean this?
Yeah.
They have I think they are showing for average, they are telling to. I'm not sure it's from this paper. So if we see from the for the VIT models, you can see they are the most shifted biased towards the shape side, and the CNNs are more shifted towards the texture side. So that shows that CNNs are having more texture bias, and transformers or VITs are having more shape bias. and because of the texture bias problem only that adversarial attacks case was there. And so it's interesting to see why like transformers do not like take that lazy route of thinking of textures and classifying images. That may be because they have less inductive bias. So then transformers are good, but there's a problem. Like we know that they have like quadratic computational complexity. So stemming out of that main problem, there are problems like this scale of visual elements. Like when we take words, we know like we map every word to an integer and then into an embedding. So that's easy. But when we come to visual elements, their scale can vary. Like they can be large or they can be small. But we know transformers have fixed size scale, like 16 by 16 patches. But now when the object is larger, we can say that there are many patches inside this, learn the relationship between these patches. But when when the visual element is very small, it will be like inside one patch. So in that case, it will be difficult to like model it. And then the other problem is the high resolution of pixels. So when the like pixel count or the resolution increases, because of the quadratic computational complexity, it will be difficult for the model. And also like when it comes to like pixel level task, like segmentation, like semantic segmentation, we need to classify to what class each and every pixel belongs to. But we know transformers are considering patches. So for a pixel level task, the patch level transform is not going to work. That's why in the VIT paper they are mainly showing it's good for classification, but it's not so good for like tasks like semantic segmentation. So as a solution to this, the Swin Transformer is proposed, and I will briefly like go through their contributions. So shifted window based self-attention. So in VITs we calculated attention for the whole image. It was global. But now what they are doing is they are like building these windows, and attention is only calculated in these windows, and there's another thing called shifted window based self-attention. We will see that later. And then through this, because now we are not calculating attention for the whole image, we are only doing in this window, therefore the computational complexity is reduced to linear. And then also we are getting hierarchical feature maps. That's done through another architectural change which they have done in this. So because of this hierarchical feature maps, we can use this Swin Transformer as a backbone for things like UNet, because UNets need hierarchical feature maps. And also because of these things, we can say this is a general purpose backbone for computer vision tasks. And also another important thing is the speed accuracy trade-off. And now we will go into depth of what they have done. So these are the different layers. So there's a patch partition layer, linear embedding layer, and these Swin Transformer blocks, and the patch merging layers. And so one like another thing you can notice is this amount of blocks they have used is always even. The reason for that is like this is one block and it should always follow by this other block. The difference, the thing is, this has window based self-attention and this has shifted window based self-attention. We will see why that those two should follow always. Okay, so each time two blocks means those two should like appear together. And now we will go into depth and see what each block does. So we will first look at these two. So what happens here is, now given an image H by W, and 3 is the channel number RGB, and we will be breaking it into patches similar to VIT, but this in VITs it was 16 by 16, here it is 4 by 4. And then what we will do is we will send it through a linear embedding layer and we will map it to a C-dimensional embedding. And since we are taking 4 pixels per patch, the size of the, like not the size of the image, but the output will be H by 4 into W by 4. But although they have shown it like this in the paper, in the implementation what they have simply done is they have sent a convolutional kernel of size 4 by 4 with stride 4. That means they are keeping the convolutional kernel which is 4 by 4, that will cover 4 by 4 pixels, and then in the next time they are having stride 4. That means they will look at the next patch and they will have C such kernels. That's why they are getting the output side C. So although this shows like this box is actually representing a 1D vector of dimension C. Okay, so it's not like this is a patch, but this is actually a 1D vector. Okay, and then when we look at the transformer block, we know like in the VIT it was like this. There was a multi-head self-attention layer, and when we come to the Swin transformer, like all the other things are the same. The only difference is this: instead of multi-head self-attention, we have window-based multi-head self-attention and shifted window-based multi-head self-attention. So what happens in this is, so initially we'll get a reminder of what this multi-head self-attention in VITs does. So we'll wait for it. So it will break the image into patches like this, and it will compute the attention to every other patch. So that's what was done in the VIT. And in window-based multi-head self-attention, what it will do is, given an image, it will, like we saw this part breaking into patches, and we will further break it down into windows. So in the paper they are saying it's M by M, and what they have used in the implementation is 7 by 7. That means inside one window there will be 7 patches in one side. That means a total of 49 patches, and then we will be calculating attention only within the window. So each patch will have attention to only the patches within the window, and like by doing that we are able to like reduce the amount of computations, therefore achieve linear computational complexity. But now this brings another problem. Now if we look at a picture like this, in order to like classify this, it needs to like identify like relationships between the features. So in order to do that, it will need to identify this is the eye, like there's a relationship between these features, like that it will need to identify. But now see, this eye is in this window, it's in this patch. This patch will only have attention to the patches in this window, but this patch is in another window. Now these two will not have attention. So now that's a problem, right? So what they are doing now they solved one problem and another problem came. They solved the computational complexity and now another problem comes. So to solve that, they are using this shifted window based self-attention. So what's done there is, we have the image like this, and the windows, they will be shifting by m by 2 into m by 2 into these two directions. M means actually they have used 7. So they will be shifting this window like this. It will now be here. So now see, after shifting like this, now these features are in the same window. So therefore these can have attention. But still see, now let's say this and this eye and the ear, in the ear it was some other feature, and these two were important to classify the image. But even after like shifting, these two are still in separate windows. But the thing is, now initially these two were in the same window, so these two have attention. But now in this window setup, these two have attention. So the model will automatically learn, okay, these two have attention in some windowing method, these two have attention in this, therefore these two should also have attention. It's like A equals to B, B equals to C, then A equals to C kind of thing. So by shifting, now what happened is the number of windows increased, right? So we can like pad this with zeros, but the amount of windows increased. So they have found that if we do some padding and do the go forward, the amount of computations will increase by like 2.5 times. So as a solution, what they are doing is, like after shifting, they will be like doing a cyclic rotation, and they will be like rearranging things like this. But now this, if you think deeply, this brings another big problem. Like now see, like we had this and we shifted, and then like this is how it will look like, patching, and then after shifting this patch will come here. Now see, this and this are in like the same window, so now these two will start to have attention, but in the actual image these two are far apart, so these two should not have attention actually. So actually these two should not have attention. So as a solution to that, they are using this thing called masked multi-head self-attention. So what they are basically doing is, now actually these two should not have attention. That means like before shifting, these two are in two separate areas, and after like shifting it, this comes here. But actually these two areas should not have attention. So what they are doing is, after doing like now normally in when we have when we do multi-head self-attention, what we do is like we take this and create the query and the key matrices and multiply them like QK transpose attention equation. So when they do that, when for areas where paths are coming from different images, different parts of the image, they will do a masking. That means like when we multiply the query and the key, like when parts of the same when they are coming from the same parts of the image, they will take that, and when the multiplication is coming from different parts of the image, they will mask it out. How they have masked it out is, they have multiplied the value which we are getting here by a large negative value like -100. So we know, because in the attention equation we have QK transpose, we are taking the softmax of that. So when we take the softmax of a large negative number, it will basically vanish. So then this is the overview of things which happen. We have the embedding coming in, and this is the flow, and these two should always follow together, as I mentioned earlier as well. And I think I don't have to explain this, it's easy to understand, it's coming and going into the layer normalization and so on. And then the patch merging. So this is where the hierarchical nature comes. Now we know in CNNs we have pooling, and this is the version to substitute the pooling. So what they are doing is, they will take 2 by 2 patches like this, and they will rearrange it vertically in the channel direction. So in that way we are able to reduce the resolution and increase the channel count. So another example here, it's initially like this, and we are taking 2 by 2 patches like this, and we are rearranging it in the channel dimension. And in that way, initially if it was C dimensional, now it becomes 4C. So to reduce the channel count, they are again sending these embeddings through a linear layer and mapping it again to 2C. So that's how this C and then resolution halves and the channel count doubles. That's how that's happening. So another problem what you might have is when you rearrange these together, what will happen? It's basically similar to pooling. Will reduce the resolution of the image, right? Although it looks like this, normally the patches will be very small, and still the meaning of the image will be there, right? So we can't think of images, but in a way that's how it will happen. So then they have used something called relative positional bias. This is coming from a different paper actually, the author of the original transform paper, Vaswan, is also a co-author of this paper. So here what's happening is, now in positional bias we know we will be giving the absolute position. In relative positional bias we will be telling for each embedding the relative position of other embeddings. So they are modifying the attention equation like this. So this B actually is the matrix which contains the relative position, and through a ablation they have shown that the results will be best when they use the relative positional bias. I will not go into details of this because this is a separate paper, so you can read the paper, and there is also a video which I have linked here. And then we will look at the computational complexity. So that's one of the main things in this paper. So when we consider a normal VIT, so we'll draw this for you to understand. So like now we have a image like this. It will be like h by w, and we will be breaking it down into patches like this, right? And each of these patches will be c dimensional. And when we break it into patches, now in this case it was like 4 pixels by 4 pixels, so we will be dividing by 4. But actually for computational complexity calculations we can like neglect those, and like so each of these will be like if we rearrange this in this manner, like each of these patches, we can think of this as a matrix like this. There will be HW amount of embeddings, and each will be c dimensional. And then we have the like weight matrices for query, key and value, and in their case they are using c by c. We know like if we want to like increase the output dimension, we can accordingly change this. And so by multiplying this by the weight matrices, we are getting these complexities. So how we are getting that, I have mentioned it here. So when we multiply two matrices like this, the complexity will be coming, we can derive the complexity from the input dimensions like this. So you can think of a 2 by 2 multiplying two 2 by 2 matrices, and you can like derive this. This has the amount of multiplications and additions which is done. So what will happen is like so what will basically happen is so we have 3 weight matrices for query, key and value, and that's why this is 3c into c, and the input embedding, as we saw earlier, it is c into hw. C means the channel dimension, and the output will be 3c. 3c means all of these, query, key and value, and the complexity is coming like this, that's mentioned here. And then after we get these, we will be multiplying the query by key transpose, and then we will be getting the attention matrix, and then we will be multiplying that also, and that's how these two are coming. If you want, I can explain it further. So, and then finally we will be sending it through this multi-layer perceptron. So what happens there is like we will be getting a c dimensional vector, as I saw earlier. Like in attention, we know the dimension will not change, right? So because we use the same dimension weight matrices. So like what will happen here is they are like now the input to this will be a c dimensional vector. They will like expand it into a 4c dimensional vector and again reduce it down to c dimensional vector. So in that way the input will be a c dimensional vector and the output also will be a c dimensional vector. That's what we know in VITs. And the total computational complexity for a mask for a multi-edge self-attention is this. That's how they are getting that. So when it comes to the Swin transformer, so instead of calculating global attention for the whole image, they will be calculating attention inside a window. So instead of HW, we will have M into M. So that's why HW is getting replaced by M. So it becomes M squared here and M to the power 4 here. And we also have this many windows. So the total complexity now will be this. So now for the Swin transformer, we are getting a complexity like this, and you can see here in the VIT's case it was quadratic, and here now it is linear. So that's how the linear computational complexity comes. And these are the architectural variants which they have got. So the Swin tiny, small, base and the large models, and in each you can see that always these are like a even number. And then when we look at the results, so for classification, this is the training setup which they have used, and these models are transformers and these are convolutional based models. And when we compare these like when the Swin transformer came, the best transformer based model was this DEIT model. So when we compare this, now you can see for this same resolution, still here this is not a good comparison because the amount of parameters is slightly high, but they have achieved a slightly higher accuracy. So and then comparing it with this efficient net, we saw last week, I think efficient net was like found through a like search for the best like combination of depth like width and all. So this is like the best configuration for the model. But for the Swin transformer, they have not done a search like that. They have basically like stacked up in layers in the way which I showed earlier. So that's why like you can see like these are almost similar, but the resolutions are not equal, therefore we cannot really compare these. So when we look at this now, like here they have trained it on the ImageNet 22K. So here you can see like when we compare this, still the parameter count is high, so this accuracy increase we cannot really like say it is an increase because the number of parameters are higher. But now when we look at this, now see the resolution is same, the parameter count is smaller, but still the accuracy has increased. So now this actually like validates that the Swin transform is working, and it is also working for image classification. And when it comes to tasks like object detection, they have used different object detection frameworks, and as the backbone they have used the Swin transform, and you can see in every case like the Swin transform is performing the best. So that's why like the Swin transform was designed, right? Like for tasks which need like more pixel level attention. And when it comes to semantic segmentation also, the framework they have used is this, and you can see the best results is using the Swin transform as the backbone. And as ablations, they have shown that using shifted windows is important, and they have got a accuracy bump like this. And so I will slightly say about the sliding window thing. So sliding window means like in convolutions we slide a convolutional kernel and calculate the do convolutions. Instead of that, we can also slide a window and calculate the attention, right? So that's what we do with sliding window, but by doing that it's much slower, right? That's what they are showing. Instead of that, using sliding windows is better, and also the performance is also better. And yeah, so so this shows the like between sliding window and shifted window, the timing constraints is shown here. Much better timing with shifted window, and also the performance is better. And like the relative positional bias thing I showed you earlier. So these are some of the resources. So yeah, that's it.
Small question. So instead of masking in the sliding self attention scenario, haven't they tried it for maybe positional encoding?
How can they use?
Like before the
shifting operation,
yeah,
with the position encoding also into the
yes,
token, right?
yes.
Yeah, so anyway the positional encoding is there, but yeah, you mean like far away points will then have less attention?
Yeah.
We have a different token, so that's what you mean.
Yes.
No, they have not tried anything like that.
And also, is the shifting always the same? how much you shift, or is it?
Yeah, m by 2, the flow of that. So the m value they have taken to be 7, like, throughout all the models.
Always shifted to a same direction.
Yeah. So like by shifting, like as I showed earlier, like to whatever direction we shift, we want to like build up at least one relationship. If we build up one relationship, this one already had attention with every other, so it will like make a combination, like a connection.
Yeah,
That's
but
what it's done.
what I had in mind was whether it will introduce another inductive bias by always shifting to a single direction.
No, but like the direction doesn't matter in this case. Like the like we can shift into a different direction. Like it doesn't matter. The shifting only like makes the connection between these windows.
The window size is 7, you have to shift by 3.
Yeah.
In that previous slide, so the masking one, we are like, what we are doing is kind of what Avishu mentioned, right? Because we are like looking at the pairs that are located far away and masking them, right? See? So in a way it's the same thing, right? Because in that graph, the mass points are the ones that are located far away. Because if you look at this for an example, like 3 and 5, so they should not have attention and they should be masked. So those are the ones that are masked, right? You will like maybe we can use positional encoding to
Yeah, so the model within the linear layers, it will figure out what it will. So here what we are doing is
It's
for
like
masking we are
hard.
multiplying with minus 100.
yeah.
So the model itself will figure out the masking value if we use positional encoding. But then again, it will be more data hungry because it will have
And also the complexity.
complexity.
Because we are learning another parameter.
Positional encoding may be not learnable, but in each and every layer, then we have to add the positional encoding. In this architecture, they have added single positional encoding right at the beginning.
But that relative positional embedding is actually a learnable one. So this will like be a matrix where now in the absolute one we have only like one value for each token, like, but here for each token it will have a value for every other token as well.
And the other thing is the Rigstormer paper we had 2 weeks back. It's after this one. So in that paper they mentioned that in the Swin Transformer, since there is no convolutions there, right? So the Swin Transformer is not very good at image restorations.
Yeah, they are not talking anything about restorations.
But then again, it is a pixel level task that they are saying that this is working.
This should
Yeah,
work.
so probably it should work for restoration as well.
Yeah.
But the Swin Transformer, the Restomer says that it's not good at restorations because it doesn't have like a local attention beyond that patch, because the conversion only runs within the patch, right? But probably it should work if it is working for segmentation.
Maybe not that good at pixel level task as convolutional things. So RESTful.
Yeah, they like integrate convolution inside that. They first do the convolution and after that make the patches and do attention.
Yeah, another problem might be like here they are, although they are telling pixel level, they are taking 4 by 4 pixels. Like initially it was 16 by 16 in the VIT, they are reducing it to 4 by 4, but still we can't say pixel level, but still 4 by 4 is much better than.
In all tiny, small, base and large versions, the hierarchical link is there.
Yeah.
No application on that.
That's
About hierarchical link, if they don't have it, what happens? We reduce the all up until each divided by 32, right?
Yeah.
All.
අතන මේ මෙහෙම පිට් එකක් තියෙනවා ඒක හරි proportional to HW ප්‍රමාණයක් තියෙනවා මේ embeddings හැම එකක්ම C dimension ඊට පස්සේ අපි ගාව මේ weight matrix එක තියෙනවා මෙතන දැන් මම query එකට වගේ ගත්තොත් ඒකත් C into C ඒ කියන්නේ එහෙම කරන්නේ අපි මේ dimension එක වෙනස් කරන්න යන්නේ නැහැ ඒකට multiplication එකේ ජර මම පෙන්නේ අර complexity එක So for the implementation I did this. So I initially took the original script which they have given in the repo and like broke it step by step, and also I did a comparison between the VIT and the Swin Transformer. So like looking at this, I am taking from the Swin Transformer these separate layers which I showed in the presentation, the patch embedding, Swin Transformer block and the patch merging. So this is the overview of the model, and what the patch embedding layer does is, as I said earlier, it will take a image like this, in this case 224 by 224, and it will consider 4 pixels as 4 by 4 pixels as a patch. So that way we will be having 56 by 56, and each of these we are mapping to a 96 dimensional embedding, and you can see this is a 4 by 4 convolution with stride 4, and we have 96 such kernels, and that way you can see finally for the 224 by 224 image we are getting output like this. So that the calculation which is happening there I have shown here. So the image we are breaking it into patches like this, it will be 56 by 56, that's coming as this. So that's the length, the amount of patches, and this is the length of each patch. And so we will be having patches like this, and windows will be like this. Each window will contain 7 by 7 patches like this. And so here I have taken the Swin Transformer block, and when we do not define the shift, it will be a WMSA block, and you can see what's happening here. So you can see all the attentions and the MLP layer here. And when we send it through the WMSA block, you can see the dimensions do not change. And also now this is the shifted window based MSA, so here we are defining a shift, and here also you can see the structure, and you can see the dimensions are changing. And this is the patch merging. So what happens in the patch merging is shown here. So like it's a linear layer. As I said, we are like mapping the it becomes 4C when we like rearrange it, and we need to map it back to 2C. So that's what's done in this patch merging layer. And also I'm doing a comparison between the VIT and the Swin Transformer, and the calls over here, and you can see the Swin Transformer's accuracy is slightly better than the VIT service.